Ladies and gentlemen, we start the final session of our meeting today. And before I give the word to Ole Andersson, just a couple of words from myself, because probably I won't have this possibility. I missed the party yesterday. I was flying from San Francisco, and I really wanted to give you some little present, just to remind you about that time we spent in Moscow, visiting all those museums in Kremlin, where you demonstrated once again how you can speak to people and make them understand you. Actually, Beria managed to touch some artifacts from like 17th century, which you're not supposed to touch, and triggered the alarm. So we were about to be arrested. And people who came, they start yelling. Of course, it was in Russian. It was absolutely impossible to explain that we did not want it. And then a lady from them, she just turned to Beria. And of course, he did not say a word. He was just smiling. And she said, finally, she was speaking so rude language before that. And then she said, please, don't do it again. and let us go. He was just smiling at her. So that was, and just because of that, so I brought you some book with all those artifacts and other things collected. So next time you know what to touch particularly.
Okay. Thank you. Thank you very much.
And now the first talk by Ole Andersson. Please.
It's a great honor and pleasure for me to be here. As I got invited, I had to think far way back. Now, how was it that it was? So I started to look up in my archives to see what, if I could find a picture or something nice about Beria. And this is what I found. So this is part of a manuscript which probably was written by Beria, the first draft, around 1977, 78, something. And but Hans was at that time at Risø. And I can see Alan McIntosh will suggested sort of a better title up here, Cohesion and Spin Polarization, Transition Metal Oxides. And then come Beria, that's all at the bottom, so it scrolls up. So Beria says, so, well, it is Swedish, of course. This is sort of a preliminary suggestion. Of course, now the whole paper looks like the Actidide paper, but what the heck, actually, it is about the same. The figures haven't been done yet, so we can have room for new suggestions, if you like. So we need an abstract and a title, but the results are great anyhow, so that is... Yes, we are happy. We will go on with it. And so the paper then started. It's very beautiful language. It must be you. Was it you, Beria? It wasn't Alan, and nobody else can write that beautiful, so it wasn't Alan. It must have been you. So here we come in recent years, the so-called mod transition, and we've heard it many times today, and it is really great. But now comes sort of the disturbing thing towards the end. And now remember, Hans was at Risø, and Beria was, what did you say, Beria? And I had just moved to Stuttgart, and you two guys had been there, and we had worked on this paper. So in the acknowledgement, two of the authors, Hans L. Skriver and Børge Johansson, would like to express their gratitude to the Max Planck Institute, Büsner of Stuttgart, for the kind hospitality shown to them during the period when the main part of this work was completed. Og så siger det, hvis Stød Hans ikke kan indrømme det, så skriver jeg, one of the authors, nej, jeg var So you can understand that those two Vikings didn't particularly like this Teutonic Germany. I had invited them to, and they have had some hard evenings.
Who wrote the last line? Who wrote the last line?
Nej, jeg var fan.
Yeah.
You did. I thought you would. That's good. Anyhow, great. But now comes the question, where did this paper get published? Well, anyhow, so it was Beria who told me about mods. And of course, it is this famous paper where Bury had let down. We heard it many times today. And this is even a shortened version of an unpublished FOA report. I didn't know that, but it says so. And that is, of course, so I had to look up various publication lists because I couldn't get the history right. So that's what I did, and this is paper number 21. I don't know whether they count, but it's sort of number 21. It has 368 citations. And then Bury, in the next years, as we've heard, laid the grounds for all that we had been doing since, certainly what Hans in particular, was doing in the late 70s. So he had the interpolation scheme for cohesive energies with Bury and Rosengren, paper by himself on the nature of the 4F electrons, number 28, generalized phase diagram. And then comes a paper by himself again where he laid out the foundation for the metallic and insulating 3D transition element monoxides and their stability. So that's the other part of the actinide story, you could say. That's the 3D story. But then this was 77, and then something came. Now, of course, came the, we've heard that many times, now came the actinide papers, 183 citations. And here's the actinide paper. Now you see Hans is still at Risø, but, well, I moved to Geneva for some reason. And so this was before Stuttgart, and Bury was in Linköping. So we were, no wonder that I can't remember what happened, because we were all sorts of places. And here comes the next one, the calculated volumes of the actinides has 0 citations for some reason. I was back in Lyngby at the Technical University, and Bury was at FOA. And here comes another one. So presence and character of the 5 D electrons again, Bury 33, that's fine. And here's the paper, it's a divided paper, and it has Niels Mortensen on it. Great, and he was probably at ETH. He was in Zurich with Wachter at that time, Mortensen in Uppsala, and I'm in Stuttgart, and so on. And another one, 2 more of these, still all these papers, 78 till 1980. Here's one written by me. It has 2 citations. And the 5F delocalization, and there were further papers to come later on. But these were most actinized. What happened to the 3D monoxides? So there was this nice manuscript, and it was really well written, and I've been looking up, and I couldn't find it in various lists. And then I couldn't find it. Here is something that I did find. Here's calculated specific volumes, and here's this nice figure of the lattice constants in the actinide 3Ds and the 3D metals and the 3D monoxides. And here's a paper with 1 citation, and it's magnetism and magnetic materials. I don't think that was a 1. And then there is another one which nobody has except me, because I, of course, wrote a long paper, but it was mostly on my own techniques and my little ways of doing things, so that is hardly cited, except for the Force theorem or something like that. And see, here I scooped Hans, because I put Hans up as affiliation in Stuttgart. So I don't think this thing ever came. The papers that ever came out with this, I put Hans as Stuttgart probably. But I think the nice paper I couldn't find. I don't know what happened. I do not remember what happened to the nice manuscript. And if it was my fault, then I offer my excuse. It's not the first time in my life I've been. But 2 papers came out, but that one, I don't think so.
I think if I look, I would know, because it's in some obscure thing.
Yeah, there were 2 obscure things.
Okay,
Or maybe 3, but this could have been a 5th letter, I would say. Anyhow, I'm now going to change subject completely. And let me just talk about some slightly more recent thing that you all love, namely DMFT. It's an early DMFT calculation. I've talked several times about this in Uppsala, but let me do it again. So the metal insulator transition in vanadium sesquioxide was claimed by people to be the prototype MOT transition. And as we got these DMFT LDA calculations to work, we have been looking at that and say, is that the way it is? So 1969, the MOT transition in chromium dope V203 by McGuan, the Bell Labs team, Morris Rice, Romania. So in this V203, vanadium is in the D2 configuration, and here is the phase diagram. As a function of doping, so it is chromium doped a little bit, 1%, 2%, 3% of chromium pressure out here. Down here is an antiferromagnetic insulating state. But the interesting ones is the paramagnetic metal here and the paramagnetic insulator here, and they both have the corundum structure that you see over here. And that is then an isostructural phase transition from paramagnetic metallic to paramagnetic insulating takes place at room temperature. This phase diagram shows what happens to the conductivity, and that's important. So the conductivity is here. Now in this case, as you go, let me say that I go from 300 degrees Kelvin and I increase the pressure, say. As I increase the pressure, so I come from the back, I'm in the insulator, I go through here, so I should maybe say that this, in this plane, red is metallic, blue is insulating, and this plane is the plane of this, of temperature and pressure, and up here is conductivity. And now as you come from the back, you see how the conductivity, as you go through here from the insulating and to the metallic phase, conductivity jumps by orders of magnitude and stays metallic like that. That is a metal insulator transition, and that was for many years believed to be the Mott transition. Now the corundum structure is a little complicated. Vanadium are the yellow, the green ones, and the octahedron are octahedron. So the octahedron are here violets. And the shortest distance is this vertical one. This one is called a vertical pair. It's a little shorter, but there are many neighbors out here in the plane, so who wins in the hopping, and we'll see. Now, why does it do that? You can look through it. So, 2 electrons, octahedral coordination, it's a T2G system. And a T2G orbital is now the orbital. This is an XY orbital with a prime because it's oriented according to this octahedron. And here is such a T2G orbital sitting on vanadium. And in this case, we took a Wange function, so you have little tails on the oxygen, PD pi antibody on the oxygen. And you even see little EGs because EGs were also downfolded. So you have little G tails. Now, why does it have little G tails over here? Because there's a distortion. There's a slight distortion related to cubic, named that this vanadium, 2 vanadiums, the one here and the one here, the pair, this one goes apart a little bit down. And down here where it goes, it perhaps gets actually some bonding between the EG and the neighboring vanadium and the oxygen. Now, in this threefold axis, you recombine, of course, the x, y, y, z, and zx, and the symmetric linear combination of the threefold axis is the A1G, which is the 3z square orbital staying this way, and the 2 EGs. So they are degenerate, and the other one is a little higher. It has an energy which is 0.3 electrons higher. Crystal field splitting, that's what you have in an LPA calculation, but what is more important maybe, there is a U, which is about 4.25, and a J of 0.7 as usual. This one is adjusted as the diex would be forced in the key calculations. So what's now happening with this? Well, Bury would of course immediately know, and that is a result, is if you have 2 electrons, and you have 2 orbitals here which are degenerate, and another one is here, you will put 1 electron here and 1 electron here, and none of that. Principle tells you to do that. And that's actually what happens. But this is not the way it was looked at for many, many years. It was believed to be a real Mott transition in which you have one band that breaks. It was believed that you have a bonding between this guy and the other one sitting up here. They make a chemical bond. Then you have 1 electron left. And that 1 electron was sitting in bands, 1 from each side was sitting in the band by those, and it is that correlated band with EG pi orbitals which makes a Mott transition. So let's now look at, that's what I was interested in, how do my beloved LDA bands develop as we go from the LDA into the correlated thing, and what is this metal insulator transition? Here's the LDA band structure of the T2Gs, and there are 4 atoms and 3 orbitals, so that's 12 bands. And I have 2, so it's 1 sort of filled. If it's not been polarized, it sits here. The crystal field splitting is this little tiny amount here. And here's a typical Hoppeck integral between an A1G and an EG pi in the same plane. It's 0.25 volts. The biggest one is, as I said, this one between the pair. The sigma, it's 0.5 minus 0.49 volts. And it is those type for hopping intervals together would give this broad band. So the bandwidth is much broader than the crystal field splitting. There's a lot of hopping, and it's a big, massive thing. It would be a metal if that's the way it looked like. Now, we did have the U, and what the U is doing, the biggest one is of course going to singly occupy those bands. You're going to have an upper Hubbard band, which is not full, so you could of course try to move this Fermi level up to about here, and that would be what has been polarized calculation would basically give you, but that's not quite what happens. So we do DMFT, and I'm not going into that, it's just adding the unsigned Coulomb terms and solving into this DMFT like an endless impurity problem. And now when you do that, you just read out of the self-energies what the various things are. You find out that this crystal field splitting gets enhanced, if you like, to 1.85 volts. That is nothing else than 3J basically. That is the Hund's split. So you're going to have such a big splitting of them. And if the splitting between that orbital and this orbital is so big, then the hybridization, you're in the ionic limit, so this hybridization doesn't do anything. So if you want to have an idea of what happens, you better kill the hybridization. I'm just explaining to you now what the bands look like. So if you kill it, then you will have the pure EG band here and the pure dotted A1G. So you're killing all those hopping intervals, you're keeping all the ones between the same orbitals. Now the thing looks like that. And what you're now supposed to do is to move this up with your 3J. So you're going to move the bottom of this one up, and it will of course land here, and you can see what's happening. And that is now what the DMFT does. If I first do DMFT, but in the quasi-particle approximation where I have the shifts, and then I have the mass renormalization. Mass renormalization you don't get with the EFT, but you get them in DFT. So the upper band here, the A1G band, you say the bottom of this one is now lying here. You shifted it to up here. It's just below the bottom of this one. The lower bands get mass renormalized by a factor 5, and the upper one by a factor 3. So that's what the quasi-particle band. And if you put in the real self-energy, if you can see it, and this is a little sharper way. So this is what it is. So here the self-energy are put in. This EG band actually is flat here. Here comes this little pocket of the A1G. Up here are the upper Hubbard bands, and all of that is a big smear. There is even a little bit of lower Hubbard bands. So that is what happens. Now the Fermi level isn't exactly as I would put it, because this thing is at room temperature, even incoherent. The A1G band is coherent, it's Fermi particles, but this one is incoherent. And now, so this was all calculated for the metal. Now, the calculation we did is for 4% chromium doping. You remember, maybe you remember the red and the blue points I had in my first picture. And now this lattice constant changed slightly, not much. There's a slight distortion, namely that this thing goes a little bit apart from each other. And that thing now has this, as these two get a little bit apart, that this thing has a drastic effect. It goes from 0.49 to 0.41. And now you see the bands, or the dehybridized bands, just look like that. So whereas here to get a metal insulator transition in a simple picture, you need 2 volts, and you had only 1.85. Here you need 1.7, and you have 1.05, so it will become an insulator. And that's actually what the T calculation also gives you, that the C is on the power. So the whole conductivity business is simply done by band overlap. 2 bands are going away from each other. Nothing like a single band breaking into 2. But of course the U has played this enormous role of these ones be that you have the upper Hubbard bands, and also it has set the scene for doing this. Besides, as I said, this lower band is really incoherent. But you look at the lat here now, I just showed not much happens to the lattice constants. These have been measured quite recently. You will see hardly any volume change of this metal insulator transition. It's not like the other case. It is simply a band separation rather than a localization transition. If you go into the details, as people have recently done with the scanning photoemission spectroscopy, you can see how this transition actually happens if you circularly around it in temperature. So the blue one, so well, maybe I should say it here. So there's phase separation, and you can see this is formation of metallic clouds. So the middle part of it is red, and the insulating part is blue. The insulating part has a chromium, and the impression you get actually, because it now seems some of these islands get pinned by the blue, so the chromium is doing an important role. Pure vanadium oxide never gets into the paramagnetic insulating phase. It's only when you add chromium, and chromium is doing something. Also, pressure is slightly different. So once you look into it in more detail, it's not that simple. Well, back to Burry's papers. We came up to paper number 45, I guess. And if I scroll to the end of the list, the one I read is number 568. Now, at this conference, we probably only heard basically about the first 100, but there are some 400s more. This is fantastic. So this is Burry's sales curve. This is his citations as a function of time. So how many citations did he get in 1900? Well, 74, he didn't get many. And it took long. But this, I've never seen any, and I've seen many, because we're always asking to write about these people so that they get their thing. But this is fantastic. And not only is Burry such a good scientist, as we've heard many times, he's very good to his people. He motivates them. So this thing will, of course, go on. He could either die, and I'm sure that this thing will keep on going for generations. He is good to his friends, as you can see. We do get our rewards from writing good articles for him and promoting him and so on. And but he doesn't have any plans about retiring, because if you have a sales curve going like that, why should you? So many happy returns, Burry, and thank you very much. And we mean it, really. Thanks.
Dear Burry, thank you. And the organizer, thank you for inviting me and to present a few of my thoughts on the occasion of your birthday. And we have heard so much about actinides and citation indices. So I would rather more concentrate to the person. And maybe I start with some biographical details. Burry was born in 1942, actually I think on the 12th of June, is it true? Yes, tomorrow, yes. Tomorrow in the province of Dalarna. This is the place where these little horses come from. So the Dalarhästerne are very famous. This is like Sachertorte from Vienna. This is these horses from Dalarna. It's some 150 kilometers north of Stockholm. And his first school years he spent in Falun. And Falun is famous for those non-Swedish people like me. Falun was a mining town since the 11th century, and it was one of the biggest copper suppliers during the 16th, 17th century. It's so important that it even entered German literature. There's an author, a romantic author, E.T.A. Hoffmann, who wrote a novel, The Bergwerk von Falun, so the Falun mine, because this mine collapsed. And no one was hurt because it collapsed on a midsummer's day. And no one was in the mine, of course, because all the Swedes were celebrating. And this is sort of a miracle. Owing to his excellent performance at school, Burry received a free place scholarship at the Sigtuna Humanistiska Läroverk, which he finished in 1961 with the highest reward of the Swedish Association of Technology for the best written exam in mathematics and physics for the high school certificate in Sweden. After finishing school, Burry started to study physics and mathematics and graduated in 1965 with the Licentiate of Philosophy from the University of Stockholm. About at the same time, he started to work as a scientist in the Swedish Office for Defense, FAO, which we have seen several times today, and where he kept working until 1979. Parallel to this employment, he worked on his thesis and received his Doctor of Philosophy in Theoretical Physics and Mechanics from the University of Stockholm in 1969. What now followed were the classical Wanderjahre, the traveling years of a young scientist. During the next 10 years, Burry held a series of positions at some of the most renowned academic institutions in Europe and the United States, which include Nordita, Copenhagen, the universities of Brussels, Stockholm, Uppsala, the Centre d'études nucléaires in Grenoble, Linköping University, Max Planck Institute in Stuttgart, and the ETH in Zurich. In 1980, he became professor for theoretical physics at the University of Aarhus in Denmark, and then in 1985, the Swedish Science Council, which established him at Uppsala University, awarded him a personal chair in condensed matter theory. During these years, he spent several times as a visiting scientist in the United States at Los Alamos, the Xerox research facility in Palo Alto, and Oak Ridge National Lab in Tennessee. Finally, 2000, Börje changed to the KTH and became professor at the Royal Institute of Technology, but remained as a part-time professor in Uppsala as well. In 1997, he was elected a member of the Royal Swedish Academy of Sciences and also became a member of the Nobel Prize Committee. Börje was and is still a member of numerous decision-talking committees and groups within the national and international physics community. In 2000, he received the finest honor of the Swedish Academy, the Celsius Medal. In 2004, he became honorary doctor of Moscow State University and only a couple of weeks later of my alma mater, Vienna University of Technology. As far as I found out, Börje has supervised more than 30 PhD theses, and he's author of, we just read it, some 560, 507, well, you once told me you stopped counting, so I don't know. It must be made, I guess it's something like 800, yes. It's more 800, so Google Scholar is not very precise on that. We heard a lot about actinides. Well, these, yes, I should have told you, these are pictures I found on the net, and I thought it's nice to have a little bit of a, while I'm talking along here, you to have a little bit of a optical substitute, anyway. Okay, we heard about the actinides, but his work actually spans a very large field, and if I have just remind you, there were things like the oxidation of plutonium dioxide, austenistic stainless steels from quantum mechanical calculations, mean field potential approach of the quasi-harmonic theory of solids, stability of the body-centered cubic phase of iron in the Earth's inner core, optical properties of silicon germanium alloys, modeling actinides with disordered local moments, stainless steel optimization, lithium work on lithium batteries, and like Halley's Comet coming every couple of years, some papers on Invar alloys. And just talking about martensitic phase transitions and steel and alloys, I had an experience as a young physicist just when we thought we can calculate everything, which is actually a quotation by Enrico Clementi, we can calculate everything. We did some paper on martensitic transitions and sent it to the journal, and we got a referee report back telling us that I don't see why we need a theoretical paper about a subject we know for the last 3,000 years. So what I did is I picked up the phone, it was Journal of Physics, phoned the editor and asked for a younger referee. And the paper was published, actually. But of course, as a theoretician, starting in metallurgy, you start grazing on pastures which are occupied by other bulls, of course. So you have to be very careful, especially when you're a young person. After this rather encyclopedic summary of Börje's career, I would also like to speak about the person. My first contact with Börje and his group happened when I received a letter of invitation for a one-week visit on the occasion of Ole Eriksson's Disputation in 1989. And I must confess, I didn't know too much about Uppsala. I showed this letter to Professor Schwarz, which we have heard about, which I heard from in the morning, and he told me, well, Uppsala physics, there's something very, very, very special. They have produced 2 Nobel Prize winners, the Simak, and I should be very proud, and it's a big honor to go. So full with expectations, I traveled to Sweden and received the warmest welcome. I was picked up at the railway station by another young scientist at that time, that was Lars Nordström, waiting for me with his bicycle and showing me my quarters, which were actually, Mike Brooks and I, we stayed at the same place with some crazy lady renting out some rooms in her home. we didn't have a bathroom, but there was somewhere a sauna on the other hand of the yard. But well, I think she showed me the sauna first before she showed me actually my room. But never mind. And I'm grateful to Mike Brooks because he somehow introduced me where to get a breakfast and all these things. So we went up to the university, and the group of Börje was then in the Siegbahn Villa, and it was beautiful. It was a very nice May. It was warm, and I was told to go up to see Professor Johansson. So I entered that room, and I couldn't see anything because Börje was still a heavy smoker, as we have heard several times. Sun was rather low, the blinds were half shut, the sun rays were coming through, but Börje was sitting, the sun came from his back, so there were just the sun, I could just only see the sun rays, which were actually diffracted by the smoke in this room. And Börje stood up with his sort of Hawaii-type shirt, came to me and said, well, hello, Peter, welcome. We invited you because we want to learn something from you. And for me, as a young just finished PhD student, this was something completely out of this world, because this was so different from the sort of professorial attitude I know from Austrian and German universities, where, well, my former rector, he always said that an Austrian professor and the Pope, there is a difference. The Pope has a boss. So now I saw Börje. So this was sort of a different thing. And this was the beginning of a friendship and a collaboration, of exchange and correlation, of course, for which lasted until, well, it's still lasting. So I became a regular visitor to Uppsala University, and on one occasion, and you have also already moved then to the old physics building, and they had this beautiful tower and the guest rooms in the tower, which I loved very much, because we could go on working and go up and down, and if you couldn't sleep during the night, you were just going down to the lab and keep on working. Well, I came to this place, and I noticed a big TV screen in the common area, where all the people met, and normally the discussions took place. And I was somehow surprised and asked Börje, well, what was that, the TV in the physics department? And they said, this was perhaps one of my best ideas. You know, there were the Soccer World Championships this year, and of course all the students wanted to see the matches. So by having the TV on the institute, they can watch the games and keep on working afterwards. Börje, in this way, always succeeded to create a scientifically intense, but at the same time very relaxed atmosphere, and I never saw him not smiling at anyone, and this thing was quoted already today. I remember a PhD student, it was Joachim Trück, who at some occasion was for some reason slightly sad, once said to Börje, "Do you always have to be in such a good mood?" And I think he has to. It's really his very personal attitude. But also as a person, he's caring enormously about students and collaborators. This means, of course, this is trying out any possibility to receive funding for his group with his scientific achievements is enormously successful in that. I once had a chat with another professor from the physics department in Uppsala and said, he told me, when Börje applies for 1 million crowns, they give him 2 million because it's just his Börje. I don't know whether it's true, but no. Maybe it's 10 and 20 now, I don't know. Another thing which I found rather intriguing was I received an invitation to his home on Sista April. I had really a hard time to find a taxi, at least a non-drunk taxi driver at that afternoon. But somehow I managed to arrive at it was still at Tomatgatan. And when I arrived, the first thing Börje did, he took me to his garden and he showed me a Kungslilie. And for those who don't know what a Kungslilie is, you have seen it today on Kai Siegbahn's Nobel certificate, actually. It's a lilia. We have something similar in Austria. It's called Schachblume, but it's very close to extinction. So I was very curious about that. But this is also in a sort of barrier. Well, the other thing was the first time for me. I was taken to an ice hockey match. So he somehow arranged to put us all to an ice hockey match, and it was the Swedish semifinals, and it was Djurgården, of course, playing Leksand. And since it's Börje's, it was quite an event for me, and then it was very impressed. And since it's Börje's birthday, I'm not telling you who won. And another one, which was rather personal, and this really shows how personally caring Börje is with his visitors, with his guests, with his friends. It was in 2003. I just was here for a longer stay, and my wife's mother unexpectedly died, so I had to shortcut my visit and take the next plane home. So, of course, I told Börje about the reason for my early departure, which I know was on a Wednesday, and the day after I received an email, already been back to Vienna, written the same day, sometime after midnight, saying, "We are thinking at you both. Take care, Börje." It's these little things which make all the difference. Thank you, in a way. Well, this is certainly a sort of incomplete account of Börje's talents. And I think I should come to an end, and I hope I could convince you that exchange and correlation, in a sense, has been important to Börje and his collaborators, and certainly in more than one sense. And you know, Börje, physicists, when they grow older, they just become accelerated slightly until they reach the speed of light, and then time stands still, so they can keep on working and stay with us for an arbitrary time. And this is what I wish to you, and I hope it will be, you will celebrate your birthday tomorrow with your family, I guess. And thank you for everything you did for me, and probably also for all the other people here in this lecture hall. Thank you very much.
My good fortune to be here today. Heartfelt thanks to the organizers. And my path to Börje began with a chance encounter with Ole Eriksson and John Wills. At the time, I had been working in another area of science. And after that meeting, I was no longer working in that area of science because I was excited about the things they had told me about. Ole told me that we needed some help. And I said, "You want me to do a calculation?" He says, "No, that's not such a good idea. We need samples, high purity samples and electronic structure probes." And so that began my career. And at the time, shortly after that, I became acquainted with Jim Smith at Los Alamos, and I adopted him as my father and began my sample making career and measurement career. And shortly after that, I attended an actinide meeting, and I met Börje, and he took the time to come over and talk to me and put me at ease, and I always appreciated that. And I also met Jerry Lander at that conference, and he planned the rest of my career, so it was okay. So these are experiments that Börje and his group really inspired. And the path to electronic structure begins with good samples. And at the time, the sample quality was not what I thought it could be. And so I began a purification program. This is works for the actinides. This is a molten charge of plutonium, and it's in a crucible here, which acts as a transformer, and the molten state is actually levitated, and you can distill off impurities that way. And this is the way I purified many actinides, and I used some of the samples to look at low temperature specific heat. Jim Smith and I measured some of these. Some of these had already been measured, but this is the electronic specific heat coefficient versus element, and this is just a generalization what Börje had said. You see localization at americium, and you get all this craziness at plutonium. So in order to proceed with electronic structure measurements, we started looking at shape memory alloys and the martensitic transition, and you've heard a little bit about that today. This is a picture of nickel manganese gallium, and this is not a trick of the camera. It's actually have a field applied to this sample, and you can see the martensite forming and the variance forming, and this is rich for electronic structure. And I also have looked at the pressure dependence of some of these, and you can see that with modest pressure you can squeeze out the martensite phase. So this is martensite phase, this is the parent phase. And so you can take this a step further, and I began to look at electronic structure probes, and the traditional ways, of course, are de Haas van Alphen and Shubnikov de Haas. This experiment was on a shape memory alloy, and I actually saw quantum oscillations in the speed of sound because I wanted a different probe to work in high magnetic fields. And so this is the speed of sound in the material, and this is the magnetic field, and you can see the quantum oscillations extend to 30 Kelvin in this picture, but I later measured the sample to higher fields in a pulsed magnetic field, and the de Haas van Alphen, well, I don't know if it's de Haas van Alphen. De Haas van Alphen is for magnetization. This is for speed of sound. I don't know what you call it, but it extended all the way up to 100 Kelvin. So we were able to measure quantum oscillations in various ways. So to get to the point of what I wanted to say, we all know about Boria's description of the alpha-gamma transition in cerium, and the Mott picture is very simple and elegant, and over the years, as you well know, it has competed, well, the Kondo picture has been emerged, but as Jim told you, the Kondo picture is built on sand, to quote him, and the Mott picture is very elegant because it works in P, D, and F bands. And you can see here that in phosphorus doped silicon, you can get transition over to the metal once you dope in enough carriers where the wave functions overlap. So it's quite transportable. It's just not for cerium. So in the cerium phase diagram, I've cut it off to lower pressures here. Boria extended this line of transitions all the way up to the melt, which was the first time I had seen that done. And later, L.A. Ashberg and Kapellman, using available data, suggested that this line AB is a line of continuous transitions, and point A is a tricritical point, and this places a symmetry breaking requirement on the alpha phase. About that time, Jim Smith and Zach Fisk had done some work in cerium thorium, which Professor Moutenson talked about this morning. In particular, Jim asked me if I could get this transition temperature down. How would we do that? And so I began work on the cerium thorium system doped with lanthanum. So the purpose of the thorium is to suppress this pesky beta phase, which is actually metastable. It's kinetically unstable. Pecharsky and Schneidner showed that it has a half-life of about 800 years. So the thorium is meant to suppress this so that you can look at this transition over here at negative pressure because the alloying expands the lattice. So when you add in lanthanum, it drives the alpha-gamma transition temperature down. And at about 14% lanthanum, we see another tricritical point on the negative side, negative pressure side. So the phase boundary for the tricritical point looks like this. This is magnetization versus temperature with increasing lanthanum, and you can see that the hysteresis goes away. And I know that it's a bit nebulous argument without microscopy data, but it is the phase diagram, the best phase diagram we can put together right now. You can also look at the fluctuation of the F electron in a large magnetic field. So it occurred to us that if we put this in a large magnetic field, and if this F electron were fluctuating on a characteristic time scale, we should be able to couple to it. And this is the temperature of the alpha-gamma transition versus field, and you can see that it's driven down in a mean field fashion. And this curve was actually fit by Guykoff at Florida. And at the time, I suppose Jim or Zach Fisk told him that we were doing this measurement, and I couldn't quite get the data fast enough because I had been up working all night. I remember I would just get back to my room and get to sleep, and I would get a phone call. I would pick it up, no hello, no nothing. Jason, what is critical field? And so I would tell him, and he would plot it, and I would go back to sleep, and we'd do this for several nights, and he fit this curve. So, but what it shows quite clearly is that you can couple to the spin and get a nice picture of the 4F involvement. So I mentioned that this symmetry breaking requirement, if you have a tricritical point, this is just a picture of FCC gamma cerium. It's a nice FCC structure with the lattice constant A0, and the stacking sequences go as you would expect. But when you get this beta phase, it's actually the same thing as the FCC structure with a stacking fault. So the stacking sequence goes A, B, A, C, A, B. So you get this stacking fault. It acts as a sink for dislocations. And so it's very close to the FCC structure. And then finally, some recent experiments by a Russian group showed that the alpha phase is actually a quadrupole ordered phase, and you get the right lattice constant. And they measured this by perturbed angular correlation, and they had to insert a cadmium-111 lattice atom. And one possible problem, as Peter Riseborough pointed out, the next speaker, is that the introducing cadmium into the lattice could actually break the site symmetry. But this is a very elegant measurement, and in order to detect the difference between this and this, you have to have a point symmetry probe. You can't rely on X-ray diffraction alone to tell you the story. So this is the best picture we have of cerium now. And in order to detect the beta phase, we've used a technique that we adapted from the shape memory materials. And if you just measure the resistivity here, you can see the temperature hysteresis of the transition. If you probe this hysteretic region very slowly, you can in fact get a noise spectrum of thermal spikes. And this is caused by scattering off the intermediate beta phase. You can look at the statistics of these spikes and get a picture of what is going on at the interfaces. And we see carrier localization at the interfaces, which is consistent with the Mott picture. And so a few closing statements. Borje, of course, has covered much of the periodic chart. And he has made several contributions, but as we've all heard, besides all these contributions, he's just a wonderful person. So I think I'll stop there.
First, let me thank the organizers for inviting me for this very auspicious occasion. It's a pleasure to be here. So, the long outstanding puzzles, I'm just going to give a list of them. First one is the gamma to alpha transition in cerium. There are several other things which I consider long outstanding. A proper theoretical description of the normal state heavy fermion in metals with a large mass. The origin and nature of the pairing states in heavy fermion superconductors. This is this is the original problem. The same problem occurs in the transition metal superconductors, etc. Hidden order in uranium, ruthenium-2, silicon-2, and the pseudo-gap state in high TC superconductors. So let me then go to the next slide, which I'm not going to talk about this very much, except we've heard that there's a gamma-alpha transition in cerium, which with its volume collapse and various critical lines, etc., that Jason talked about. From the theory point of view, the first suggestion was the promotional model by Zachariasen and Pauling independently in 49, where they basically suggested what happened in this material was that the 4F level was degenerate with the conduction band, and so it was very easy to squeeze electrons out of the conduction band into the F band, at which point there's a decrease in bonding and a volume collapse, etc. And of course, the occurrence of more magnetic F character. So this was the original picture. However, as Bourrier said in his paper, there was experimental evidence to show, this was Dan Gustafsson, who showed that the number of F electrons didn't change. And as he said in his paper, you need a radically new interpretation of the data. And so this came out in his paper in Phil Mag, which we've seen a number of times. I don't think it's the wrong journal, I think it's the right journal. Cited 384 times. If you'd published in PhysRev Letter, so there may have been more, but the follow-on for this, which is the Kondo volume collapse model, has a very similar number of citations the last time we were looking. So I would say that this is a pretty good journal to publish in. Okay, so anyway, I think this thing has really stood this test of time. As Jim Smith mentioned, the Kondo volume collapse model was basically organized around a single impurity model. It was about this time that I first met Bourrier. He actually was doing part of his world tour with the promotional model. I think he'd visited Paris and talked with Coquelin and Blandan and politely explained to them that their version of the promotional model, published in Advances of Physics, which is a spin-off of Phil Mag, was wrong, etc. So he walked into the lion's den and escaped that intact and stronger than ever. So he then came to Imperial and gave a talk. That's when I first met him. I was a graduate student. I think he came to Imperial because he wanted to see Neville Mott. Neville Mott was at Cambridge, but he also had an adjunct appointment at Imperial. So he was in a state of valence fluctuations between the two sites. And so I think that's why Bourrier came to Imperial, and that's when I first met him. And yeah, I really enjoyed that talk, I must say. I'm looking forward to your next one. Okay, anyway, so having said that, let me skip over a lot of problems, and basically what I want to do is to look at a hidden order problem in uranium, ruthenium-2, silicon-2. This is, I think, a problem, it's very, very specific to uranium, ruthenium-2, silicon-2. It's been hanging around since over 25 years without a solution. There's been a number of suggestions. This is a material which I think somebody mentioned about, has strong correlations. And when you get strong correlations, like in the one-dimensional Slater-Hubbard model, you get gaps. And this is what this is all about, is a material where as you cool it to 17 degrees, you see this huge spike in the specific heat, this lambda-type transition, and at lower temperatures, there's a superconducting transition. At 17K, a gap opens up in the transport properties, and you can actually see it in optical conductivity. So there's this huge gap. Everybody assumed at that time that this was magnetism at work. However, it was not magnetism in the usual sense, because neutron scattering couldn't show anything. That's why this whole thing is called hidden order. Recently, some new clues have been thrown into this. Looking at magnetic torque experiments, you can see that there's a clear change in the isotropy of the system. It's actually a tetragonal system, so there should be a symmetry in the AB plane. However, at 17.5 Kelvin, there's a change in the anisotropy. These are two experiments which show that at the low temperature phase, if you look in the plane, you see that there's a icing-like anisotropy in the G factor. So there is some sort of magnetic thing there, but no net magnetic moment. I'm just going to skip over this because, so this is a bold suggestion, hopefully like Bourier's, of what's happening is that there's a gap opening up on the system. However, I don't think this is, the magnitude of the gap is only 10 millielectron volts. This is not a very large gap, so it's not a Mott transition. However, the suggestion is that if you take this spin rotationally symmetric model and you look at the Hund's rule coupling, and specifically the spin flip contribution for that, you can have a breaking of the Hund's rule rotational symmetry breaking, whatever I said, and get a new order parameter which actually mixes the two, mixes states of different orbital characters. For an example, if you think about the three T2G levels in a transition metal in a cubic environment, then of course they form independent bands and they would never mix. What I'm suggesting is that in this F electron system where you have two F electrons is that there is a transition where you do start mixing these two states via mean field theory, and essentially what you end up, if you just take the Hund's rule expression, do the mean field type linearization of the interaction, then you can ask yourself, what happens if the interorbital coupling for upspin electrons is of opposite sign for the downspin electron? You get an energy lowering, and then you get a spin-dependent hybridization between these two different orbital bands, which obviously just breaks open a spin-dependent hybridization gap, and you then end up with a pseudo-gap state, because you don't, well, to do this properly, you need some sort of nesting, and there's some, and I guess this is also part of Bourier's heritage, having established these groups in Uppsala and KTH, that Peter Open-Ear has done some calculations which show that there is actually some nesting between two bands of pure orbital character in the 5F materials. And so I've just taken that from his work, which sort of suggested that this mechanism can work. If you then do the mathematics and the mean field approximation, you get nice mean field sort of band pictures. This is the so-called hidden order gap as a function of temperature. Sort of matches quite well with experiments. And as you can see, at least from the calculations, it does produce a pseudo gap in the density of states. There are states which run through the Fermi level. Anyway, so a quick conclusion then is that Bourier has had actually a large impact on condensed matter theory. And as far as the hidden order transition is concerned, he also has had some indirect input into this. And what I'm suggesting here is that systems with more than one occupied 5F band, you can actually get a hidden order state which is due to a spatially inhomogeneous mixing of bands with different character. And well, so I think I'll end there. Thank you very much.
My name is Ivan. I'm from Pennsylvania State University. I was in the Uppsala group during 2000 and 2003. During that time, I didn't solve this problem, but I kept the problem in my mind. I think I solved something. I'll show you what's in common between the two. I think if you handle the thermodynamic properties for these two are same. They can handle the same basis. You know, a lot of presenters in the morning and during the afternoon just show some model, but I want to see something here that I can make this one quantitatively. So I will show you how negative thermal expansion is predicted by the calculation. I mean, first the principle of calculation, how the critical point was derived for theorem. Oh, this one, I think a lot of previous speaker already talked it. But for me, I don't mind this one. But I don't understand the very deep physics here. But to publish a paper, I must write this kind of stuff. Oh, this one is about the Invariant. You know, for this one, I will show how to get critical point. Of course, volume equation of state. You know, when I was China, my duty was to provide the equation of state for the F electron system at high temperature. So I read a lot of literature. I found our paper about the F electron involved a person. His name is Boy Johnson. I know who is that. So I wrote the letter. So finally I got accepted to do postdoc research in Uppsala University. So this one, I think there are both. This one also found by Bridgman, I think, the alpha gamma as a structure transition. Oh, this one, you see here, theorem also was born in Sweden and continued by a Swedish scientist, Boy Johnson, makes more famous. So this is our model. Because some people there are working on some serum alloy, I mean magnesium alloy, adding some rare earth elements there, some produce some special properties, but you need to do some research for the pure serum. So here we figure out a formulation starting from the fundamental physics. You can simply write the pattern function as a summation of individual magnetic state. Here, talking about limit to the spin up or spin down, flipping. See, you have supercell, 100 atom, doesn't matter. Then you have spin configuration about 2 with power 100, but that's huge. You might calculate using a very smaller one. So make summation here. But here you turn out this term is some kind of Helmholtz friendly for individual phase. So, you know, this function quite easy to write out, but take logarithm, derive the free energy. Then we derive some formulation like this way. It turns out to be very simple. You see the total free energy, just a little bit summation over the individual magnetic state plus this term. Look like just ideal mixing, but you know here X sigma is decided by the individual, you know, Helmholtz friend of individual phase. You see here, we write here. Oh, here talking about the relationship between Boyer's model. You know, here this paper is by Boyer, Eagle, and many others. We find a solution for that. You know, originally by Boyer's paper, look like this some kind of parameter to be optimized. It turns out this one can be calculated, predicted directly by the friend of the individual phase. So this summary, you know, by such a way, you see you got a configurational entropy. You can call it magnetic entropy, but this one only counting about spin up and spin down. And this term is about Buck modulus, is about, you know, configurational or magnetic contribution to the heat capacity. But we first did a simple calculation. We treat theorem, of course, do a calculation because due to strong correlation, we tried one non-magnetic configuration, tried one ferromagnetic configuration, and tried the anti-ferromagnetic configuration. And using that formulation, you can derive the friendly curve. You see at low temperature showing here with double well, some term is double well, is called miscibility gap. Then with increasing temperature, due to that configurational entropy, make the double well disappear. Until here, we got critical temperature. Turn out, this is quite amazing. We got about 2 GPa, the critical point between the gamma phase and the alpha phase, and those temperature and slope, everything. Here, write everything in the volume term. So this is our result for theorem. I show model result. I think we both this is something we solved the problem. Here talking about the distribution among different states. Here we specially show the configuration of magnetic heat capacity. This one look like amazing, because for other systems I didn't get this one. Especially for this one, talking about entropy change between two phases. This measure the lattice contribution, the total entropy contribution. There you see this is our calculation. After we solve this problem, this shows our prediction for the Buck modulus for different pressure as function of temperature. The black dot has some from experimental result. Here, then we go to think this kind of mixing between multi-magnetic states. We can apply this idea to Inva. I learned some terminology from Bape Lab. He was sitting here. That time he asked me about a question about this material. I cannot solve it. But after about 5 years, I think we got a solution for this one. Basically thinking about, we use the supercell about totally about 12 items, but only 9 are in there. A total configuration is should be about 512. By reduced symmetry, we got about 37 structure, I think. So see here, the calculation here is a totally ferromagnetic state, and others just different spin flipping. You see here, basically you can understand here negative thermal expansion is due to excitation to other magnetic state. But how make this one numerically? So we use still same formulation. This compared different understanding. I copied some, sorry, I forgot to write original references here, but I should, in our published paper, we have the citation. This one, I think from Peter Moore, from his paper, I copied this understanding. The difference here is that by the DL model, all the states possess almost same energy, but this, by the calculation, our calculation showing different state, we're showing gradually increasing energy with smaller volume. I think this equals calculation. I learned a lot from that paper, inspired me about do full calculation for consider all the magnetic configuration. So this is what we got. In our calculation, we saw Inva also some similar behavior like theorem. We see a critical point below its critical temperature. It's really the miscibility gap. That means double well along the fringe curve. Above that, I forgot to mention, in theorem also show same behavior. Above this one, transition between these two phases becomes second order. This is exactly predicted by Boyer, I think by the previous speaker. So what are this? Okay, this one shows some boundary here showing, I think the so-called Inva high temperature may be called paramagnetic phase, and for low temperature one may be called as the ferromagnetic phase. So this is the prediction for our volume dependence with this model. The model is based on the first principle calculation. Of course, this vibration term I determined by lattice vibration, using the Debye model. Here, compared to experiment, you see negative thermal expansion is precisely predicted. Here is showing the linear thermal expansion coefficient. Here showing the magnetic heat capacity. Okay, happy birthday to Boy.
Swedish Academy of Science and a member of Nobel Prize
Committee for Physics. We are happy to have you as an honorary professor of the National University of Science and Technology, MISIS, who has successfully promoted our scientific cooperation. We are wish you new scientific achievements, every success in life, and your creative endeavor. Dmitry Levanov, rector, former rector of our university. He is now Minister of Education. And another thing, I have to give you small medal, gold in of our university.
Oh, thank you. I don't know what to say actually, because this has been an overwhelming day, and I first of all would like to thank the organizers for doing this, making this as an event. And I think, actually, I always thought, okay, you better celebrate your birthdays, because then before you die, at least someday somebody will talk well about you. Maybe when you're dead, they might also do it, but then it's not so fun. So I really think I encourage everyone, if you have a chance, which occurred now to me, take it, because I never had a day like this where everybody was nice except Jerry a little bit, but but that was expected. And still, I encourage you to come. That because I heard they wanted you to be here, and I said, well, no, really, Jerry. I love you and your work. Yeah, it's not so easy to know what to say, because you feel all the warm feelings coming, and it's just wonderful. It's just wonderful. And I've been thinking a little bit about what should I say here now before we go on the boat. And of course, I had a few small comments about. Actually, you spoke about gold cadmium, didn't you? Gold zinc, but okay, you could have spoken about gold cadmium, because gold cadmium is also a memory metal, which was actually discovered by a Swede, Ölander, at the Stockholm University in 1930 or something like that. Just for historical things, because we tend not to remember these things, and Ölander did a good job. He found this effect. You heard this, I guess, yes. Yeah, then there was another remark that I went to Imperial College to London, and I'm just now taking up small things here, and to see Mott, and no, of course, he was not in Imperial. I wanted to see Peter Wolfart. Peter was my destiny then, because Peter had troubles with, at the time, with itinerant magnetism in nickel, iron, cobalt, and so on. So I thought it was a good friend, because we had similar problems. And he thought my case was much more difficult than his, but because I was speaking about itinerant electrons in cerium. And why did I do that? Well, you see, there's somebody, Kalle, where are you here still? Kalle Berggren talked about the time when we were at FOA. We had a considerable freedom. And I think That was wonderful, except the salary never increased. It was, it was never increasing, but still I think we got a chance to really dig down, and I think I still use some of the knowledge I got in the 70s because, well, if you see good experiments and remember the results, I mean, they are not wrong. Yeah. And then you had this freedom, and except that I was told, why don't you try to do something with magnetism? And I thought, okay, magnetism, lanthanides, okay. So I started to look at lanthanides and read the literature. I was pretty young and read the literature about lanthanides and got the... After a while, you always get interested in it, but first you think, oh, this, I don't know. But when you read more and more, you get interest, and I did. And one thing which was popular at the time was the valence question, valence fluctuations, valence transitions, and that sort of thing. And in order to have valence transitions, of course, you need to know the position of the F level relative to the Fermi energy. I mean, this is a very crucial parameter for valence fluctuations. You really need to know it. So I read some literature, I got some ideas, and I saw that I could even do much better than what had been published, for example, by Herbst. You know Ian Herbst, of course. But because I didn't use any calculations, I used just experimental data, and then you could actually calculate the position of the F level relative to the Fermi energy within 0.05 eV accuracy, something like that. So I did that, and that was also when I met Mårtensson. Because Niels, he came from the Uppsala with the ESCA, and he talked about some shift in mercury between the atom and the solid. And I said, because I had some experience with the rare earths, I said, think about cohesive energies. Maybe that helps you. But I didn't care because I was totally focused on lanthanides. I mean, this is something I remember so well. I couldn't care less about any other metals in the periodic table. And then it was later. I don't know. I don't remember the occasion, but I think there was maybe in connection with the first core level shift. Was that in gold, citrine, and then I remembered that I had been, because Niels Mårtensson, he was working with my colleague sitting next to me, but being from Dalarna, of course we talked. But anyway, we were not really working together. But then I remembered he had something about the shift between mercury and in the atom and in the solid. And so then after the core level shift, I thought, I can do this very easily. So I calculated the shift. It takes only about 10 minutes or so when you when you know these things that goes into it. So I calculated the shift, and I called Niels. I think it was Friday afternoon. Now I don't remember the number, but I mean the shift. Maybe I calculated 7.3 EV. And Niels said, no, this is not what I remember. It's something like 3.9. Numbers might be totally wrong. You're here, but it doesn't matter, Niels. And so I was, that can't be true. But anyway, I was a bit disappointed. This was Friday afternoon. And I had a weekend. I didn't think about this. Monday morning, in my office, early in the morning, who was sitting in my office? Niels Mårtensson, because then he had realized he didn't remember the number correctly, because I talk about the shift between in the free atom relative to the vacuum level and in the metal relative to the Fermi level. And he remembered, he also took into account the work function. But anyway, so when he did that, I think it was right on, more or less. So then he was sitting in my chair in Stockholm, and that started a fantastic collaboration, Niels. I think we had a fantastic time. Niels wrote his thesis. I think most of the publications was actually in one way or another with me. And I don't know, was it 23 articles or? You don't know? More than 30. Okay, we come back to that. A little bit more than 30. Okay, and we probably, I don't know how many we have together. And then because doing this work, we had to call. I was in Stockholm, he was in Uppsala, we had to call a lot. And then I remember when I got his thesis, which was like this, thick. And then he said, what could be more appropriate in this case than a telephone catalog? Because we actually, many have referred to my telephone calls, but this was not that expensive, I think. Uppsala is still. Anyway, it was a wonderful experience. And later, of course, when I came back to Uppsala, and I got Olle as my first student, and I also could use Hans Skriver. He helped a lot, as well as Ole, who also helped a lot. Because what I did, when I didn't know what to do, then I said, Ole, oh, you have to go to Copenhagen and learn. You have to go to Stuttgart and learn, and things like that. Karlsruhe. Yeah, Karlsruhe. Yeah, Mike. For God's sake, Mike, where are you? There you are. Anyway, so then I remember when Ole presented his thesis, one of the we have a committee, and I talked to one of the committee members 2 days before the examination, and I talked to him, and he said, well, I talked about Ole's dissertation work, and he said, why did Ole send 2 copies? I said, dear friend, it's part A and part B. And I think the number of publications was 37, Niels. I think you were beaten there. But a record is always a record, and then somebody is always coming from behind and beat you. But of course, I'm not sure that one should be proud of these numbers, because later I heard we have sort of destroyed the market about thesis in Sweden, that we demand too much. But Ole was very receptive. You had 3 supervisors. He couldn't avoid to do this number of publications. So why do I speak about this? Yeah, one thing. One thing I asked Niels about one of the figures we made in this article in Physical Review, which did not hit the Physical Review letters, but unfortunately, you sent me a copy, but when I copied your copy, it shows the whole page, and it takes a while before you can really show the real part. I thought you were, I'm really older than you. I don't know how to do this, but anyway. But the thing was, do we have? Black will do. Oh, because somebody also asked me, what are you most proud of? Oh, I don't know. I'm most proud of. That's very easy. I'm most proud of the students, all the students I have had, all the postdocs, all the collaborators who have been, especially, you should not say especially when you have children, but especially when those visiting in Uppsala. But still, there are moments in your science. And Niels and I made one figure. So on one axis you have experiment, and here you have theory. And if you want to have perfect agreement, this is a 45-degree line. And we had, maybe Phil, you know how many elements we were looking at. how many metals do we have in the periodic table? I mean, they were there. Every metal was there. So you could see, you should read that article and see what good agreement means. Actually, you could actually start to use measurements in the metal, for example, and tell exactly what it would be then in the gas phase and things like that. It's perfect, this. And the thing was, and why am I proud? Well, I'm proud. But it was a rather, which I didn't know. Niels knew, of course, but I was at FU. I was totally focused on length analysis. But I didn't know that this was a rather popular and heavily investigated thing at the time. And we had competitors who had real computers, and Williams was one of them. Art Williams was one of them. And they, of course, when they published, they could do it in physical letters. But what we did is much more accurate, and we didn't do a single calculations except plus and minus. You could just go to a book and read what is the cohesive energy for copper, and then look what is it for zinc, and then you just combine these numbers and a little bit of what an impurity term, which normally means nothing, and there you have the shift. So what could you do? So this is another problem which I should tell the young one. If you do a theory, don't make it too simple, because then everybody can use it without without your help. And well, anyway, I think we got pretty good attention to this paper, because after all, we covered the whole periodic table. And Niels was actually the one who realized what a surface core level shift that can be interpreted as the surface segregation energy of the Z+1 metal in the metal set. So I wonder why I didn't make that. You were really clever there, Niels. Let's see. Yeah, another thing which if you're referring to experimentalists and things like that, is of course, it's wonderful to work and sort of interact with experimentalists. But I do remember the following, that when we made the calculations, we, but when Hans and well, it was really Hans who made most of the calculations, Uli. Yes. we made sure he used the right configurations, that's all. Anyway, when you do these things, I really loved that plot of the atomic volume, because you probably don't realize what it was like in the 78 or something like that. I was sitting for half a day just looking at that graph. I must say, maybe you should feel ashamed for saying that, but I think sometimes you have really to sit down and feel good. And that I did for these actinide volumes. And then I went to conference, and I went there, and I was very proud. I stood up and showed, look at this. Oh, yeah. And then people, they were a bit happy. You know, we had this localization between plutonium and americium, and they were a bit happy. But Börje, you're doing all the calculations in the FCC phase. I mean, this is not true. Okay, it's not true. So then you go back home and you find a student and you work for another 10 years because the crystal structures of the actinides, as you have seen here, are terrible. And at that time, they were not even terrible. They were really terrible. Per. So Per was a victim. Per Söderlin, he was a victim. He actually started all these calculations for the true structures. And I don't know, you didn't talk about it, but actually doing that, and of course, if you have a good theory, it should work, and it did. So we could reproduce the low temperature crystal structures. So then you go to the next conference, and you come, you show, you have atomic volume, gold stuff. But now you have the appropriate, you could tell for each element what theory said about the crystal structure. And it was perfect. And then people said, well, experimentalist. Okay, it's good. But, you know, they changed with temperature. So then you go back home, and then the pair has left. So I think you have been doing quite a very nice work on this question about the crystal structures with temperature. But this also shows a little bit about if you're doing theory and if you're far behind experiments from the beginning, they really treat you like shit. No, I love them. And I think I think this interaction which you were talking about is really what, when theory and experiments are sort of starting to be on the same level, you have an ongoing conversation back and forth. And what I was talking about was we were far behind, and of course they wanted to encourage us. But I don't know how much I know about supervision in
The auditors still stay the same.
Pardon?
Us being above you. We wanted to encourage you, but not too much.
No, I mean, that's another trick you have to remember if you're going to be a scientist, and is that don't be too good. That is also something you should avoid. Let's see, I had some view graphs. No, don't worry. Yeah, this one, you saw it before, and I think this is the original figure. This is just to show you the evolution that has happened since I started around 1963, 4. At that time, the periodic table for a theoretical physicist looked like this. And you know periodic table, it's really periodic table. All elements were the same, electron gas, that was all we could do. Maybe we sometimes could compare with lithium and the potassium and things like that, but not much more. Aluminum, not too bad, but this was the beginning. So this is how the periodic table looked like for a theoretical physicist when I started. And now, is it almost 50 years later, it has changed. So I think now the periodic table looks like this. On the other hand, thinking about how we can treat the whole periodic table now with, especially thanks to density functional theory, I think in principle we are back to the old, the previous picture. It is a periodic table. They are the same. Density functional theory, you just apply, do the calculations. They are all the same. So somehow we are coming back to the original again. But it has been a fantastic tour through all these years to realize, because we could do nothing in the 60s. A little bit dreaming and thinking about maybe in the 50 years' time you can do something. Yeah, I thought I should also show another thing here that, okay, you can do a lot of calculations and do that, and it's fine. And, you know, sometimes still it might be good to think. And I would like to show you here, you know, if you have a D band, you have place for 10 electrons, and then the crystal structure is very easy. You start with the early, and you go through like this. And you see the structures. And then everybody says, iron, cobalt, and nickel are so different. Oh, correlations, whatnot. However, there is another way to look upon it. Say, if you just for fun, you say that these elements are saturated with magnetism, ferromagnets, for example, meaning then that you fill these 5 spin-up states, and then you fill the 5 spin-down states. So then here, the relative filling of this band correspond to something here, and it's just a factor of 2 or in terms of electrons. So nickel, you should have 2 elements. Nickel, if it's spin polarized, you take away 1 electron. In the series below, it means that you have to take away, it corresponds to palladium and rhodium. You see that because here you have 2 spin channels, cobalt like that, and iron like that. And you know this pair. We did this already in 96, 8, well, anyway. And the funny thing is that even, you know, you can look upon various alloys, and you can also determine the critical concentration when they go from one phase to the other. And you compare the similar transition if you do it between iron and cobalt. Same numbers. It works almost too good because we know it's not fully true. Another thing which you then from this simple thing can do, so this is just a band filling effect from the itinerant picture point of view. Another thing here, if you look upon the cohesive energy through a transition series like that, it's this parabola. You have 0 and 10 d electrons, okay? Everybody knows. And then you also know that the surface energy is going to be some fraction of the cohesive energy because the nearest neighbors of the surface are reduced compared to the bulk. Of course, we know it's not right and so on, but this is the first. Then you know, so the fraction here, the surface energy will be something like this, okay? Now, if we do this for this element here, when we have first fill here, then from here to there, you will have, well, we'll do it here. You have one parabola for the spin down and another one for the spin up. Okay, and then of course, the surface energy will be something similar if you have saturated magnetism. So you would expect something like this. However, we know that they are not completely saturated magnets, so in reality, the values lie something like this. So it's, again, with a simple model, might be a little bit more fun to do that in order to see what the full-blown calculations are doing. Another case which I like, and let's see. I checked the number of citations. They are about 22 or something like that. Not so impressive, but still. I thought it was going to be 0 or something like that. It's the following. You know the Hubbard model. And I was reminded, where is Oleg? You gave a speech, and I was reminded about what I did about in 70 or something like that. You know, you have the Hubbard model. You say we have a one-dimensional system, and at each site we have just, for simplicity, we have 1 electron. And then we know when we have 1 electron is coming here, it will feel U. You know this famous U. So when we are looking upon the potential, we remove this one. So when it's moving here, it will feel U here, U, 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 and here nothing. And U, U, U again. So you have one particle is moving in this potential. And you know, if you have given courses in quantum mechanics, you know, after half an hour you solve the problem particle in a box. So you solve the particle in a box, and you know that when U is larger, now I don't remember the M and whatnot here, but this is exactly, you can translate that in terms of bandwidth, exactly the Hubble thing. So this is how 1 electron sort of creates its own hole. and that makes this bound state. Another way to look upon the Hubble model. So if you didn't do that, it can be instructive. Let's see, something more. Are we short of time now?
Yes.
You know, when I was doing this work on lanthanides, one of the reasons was, of course, I said valence fluctuations, and I thought here, you know, when you are 30, you love also to have some cheap publications. I mean, a publication which doesn't take too much time. So I thought, I read about Zacharias and Pauling, and of course everybody is impressed by the names. And they told us it's a valence transition from trivalent to tetravalent. So I thought, okay, I'll do my little scheme with an F level relative to the Fermi level, and I'll make a paper in 2 days and publish. You know, sometimes it's good. But so I did the calculations, and I found the appropriate energies. And for God's sake, this energy difference between these two valence states, it should have been almost zero. It was 2 eV. So all my plans about writing a simple article disappeared immediately. So I had to start to think about what's going wrong, what's wrong with everything, and that was actually why I came up with this work on cerium as such. And it so happened that actually the title I had thought of sending into philosophical, well, finally I had some PRL, you know, but finally I thought I would say the alpha-gamma transition in cerium as a MOT transition, it's quite different. But then I had sent this, the title of the talk to KTH, I think it was Östen Rapp who was in charge of the colloquia there, and he probably misread everything. So when I saw what I was going to talk about, it was the alpha-gamma transition in cerium is a MOT transition. So then I decided, yes. So, well, actually, I probably might have thought about it, but I got more courage that I think somebody there is, what was it, the Pope had the boss, somebody has the boss there. Let's see, something else. Yeah, maybe here, for these two phases, there have been recent experiments, and I'm sorry that Michael Krisch could not come from ESRF, and he was involved in both measurements on the alpha phase and the alpha prim phase. And I think you, Ingo, you were not asked, well, we didn't know that he couldn't come until a few days ago, so I don't know. But because Ingo did the measurements for the alpha prime phase, but Krish was still involved in that one. But anyway, there they measured the phonon spectrum, and they agree very well with what you get from density functional theory in phonon calculations. And for the alpha uranium phase, Jerry, have we published our paper before yours?
No, but I mentioned yours.
That's okay. I'm not after you. You're my best friend. Because you understand what it means. Because what we see in cerium in this alpha prime phase is exactly what this fellow is talking about concerning this softening of the peculiar mode, which is actually, we tried it also for praseodymium, that we don't see anything in the alpha uranium phase for praseodymium, nothing, and so on. So it's, I think it's a very good signature of itinerant behavior in this particular case, at least. So this is something which, and this comes now, so we have I had two publications recently on cerium. I mean, this is really returning to good old times with a very good message. I think, at least I had to tune down because I wanted to say, listen, now it's proved and everything. But then, referees, they would never buy that. So you still have to say that, okay, this speaks a little bit in favor of whatever. So if you read those papers, read it much more like, this is it. This is the answer. And I should also say that in that, the theoretical collaborators in that particular work was Evas, who is no longer with us, most unfortunately, and Kim Duck, sitting here. Yeah, that was... And then another little thing we did was on copper and the different chemical compounds in copper, and it so happened that if you treat the copper surface with some hydrogen gas treatment and so on, and make a picture, is anyone, maybe you're preparing for the tomorrow's talk, tomorrow's dissertation. Anyway, it's a beautiful picture. This is a copper surface. Fallen. Who talked about fallen? This is fallen in its beauty. So this is fallen, yes. Some recent work, very recent. And this was a cover page in Pinos. So there are certain things you should be proud of. I don't know that. And then we do, I want just to see that we have been doing some work on fuel cells, and then we thought we had a very good proposition for, it was Pinos again, for the front page, but it never made it, because here we have a fuel cell, and here we have whole Stockholm, beautiful Stockholm, being electrified by fuel cells, but they didn't buy that. But you have to try. Okay, is there anything else I should say?
The bus is the next thing.
Oh, the buses, yes, of course, they are important. Very important. We have understood that. Should I say something more?
Yes, actually, they bought their bottom half.
What do you mean, the boat?
Yes, it was used.
Oh, you mean the boat is somewhere here?
Without Stockholm, it was published.
Oh, you mean it was, yes, yes. Maybe some questions, or maybe they are not even allowed. Maybe some people are not allowed. But really, it has been a wonderful and a tremendous journey over all these years, starting with electron gas, many particle physics, and phase transitions, and all kind of things. And then also realizing that the periodic table is a periodic table of elements, and that has been going on for quite a while, and I'm so happy to see all of you here. Thanks so much for coming, and thank you for all these beautiful words which you told me before dying. I'm really happy to see all of you. Thank you a lot, and thank for all the gifts. Please, thank you.